Welcome to Cpp.chat, the only podcast that you're currently listening to for C++ developers by C++ developers. Before we continue, as usual, I'd like my fellow host, John, to read this week's disclaimer.
Thank you, Phil. Welcome to the Cpp.chat podcast. Please review the following terms and conditions considering your use of this episode. By accessing, using, or downloading content from this episode, you agree to follow and be bound by these terms and conditions. Cpp.chat reserves the right to change these terms and conditions from time to time at its sole discretion. Therefore, you should periodically visit this page to review the then current terms and conditions to which you are bound. In the case of any violation of the terms and conditions set forth herein, Cpp.chat reserves the right to seek all remedies available by law and in equity for such violations. These terms and conditions apply to all uses of Cpp.chat, both now and in the future. Hey, sorry for the late start, guys. We have some extra excitement because we have managed to convince a guest on very short notice to join us. But I'm really excited about this. This is David Schwartz. David is the CTO at Ripple. He was a CppCon plenary speaker in 2016. For those of you that don't know anything about Ripple, we're going to talk a little bit about that. But Ripple is a technology that is a platform for cryptocurrencies. So, David, what should I do with my Bitcoins?
Well, I mean, I guess there's sort of the serious answer and the flippant answer. I mean, the serious...
Let's start with the flippant answer and then get to the serious answer.
Right. Well, I mean, the flippant answer is hold it until the price goes back up, right? I mean, because if you don't think that's going to happen, why did you buy them in the first place? But I mean, the more serious answer, particularly for people who have life-changing amounts, you know, people who bought very, very low and who have watched it go up and then back down, is that you have to rationally manage risk. And ideally, you would have had a sort of risk plan before you put a whole bunch of money in. If you put a small amount of money in, you know, hey, you know,
that's your risk plan, is I only put a small amount in.
Yeah, exactly. And I think there are a lot of people who only put a small amount in without a risk plan and then wound up, you know, in January with life-changing amounts and suddenly realized that they kind of should have thought about, you know, what they were going to do with it. Yeah.
All right. Well, I put a small amount in and it didn't become life-changing, but it's fun to watch.
It definitely is. It's very dynamic, right?
Yeah, right. So let's talk a little bit about what Ripple is, because there is a currency, but that's not the same thing. I mean, there's a Ripple currency.
We prefer people would call the currency XRP so that it doesn't get confused with Ripple, which is a company. It's unfortunate that the terms have been in the past not as clearly separated, and that has caused some confusion. So I prefer to talk about the currency using the term XRP and the company as Ripple, just so that there's no confusion about what we're talking about. Ripple is a traditional company. You know, we're based in San Francisco. We have employees, we have stockholders, and so on. And XRP is a digital asset that people can hold and trade much the same way you can Bitcoin.
Okay, all right. And so, but there's no company for Bitcoin. So what is it that the Ripple company is doing?
Right. There are numerous companies that are doing various different things with Bitcoin. There was no company really associated with the early day technological development like there is with XRP. What became Ripple was an early technological developer in the technology. XRP existed prior to Ripple forming as a company. It was developed by myself and a couple of other people as a technology. And then what we needed was some way to sort of build an ecosystem around that technology and bring that technology to the public. And so a significant amount of XRP was gifted to the company. And they continue as two separate entities.
I see. So what is the what is the difference between Bitcoin and XRP? What's the value, or why would I consider one over the other?
Well, Bitcoin was the first cryptocurrency on the market, and XRP was developed later, looking at the technology to try to see what are the use cases, what can we do better. I guess an analogy I like to use is the Ford Model T. There were numerous technological developments prior to Bitcoin and prior to the Ford Model T. In the case of the Model T, you know, the developments in engines and fluids and suspension and tires and materials and transmissions and gears. And we got all these little technologies, and people were like, oh, that's cool. We'll use the engines maybe in a factory, and maybe the tires will make our horse carriages, you know, more stable. But then the Ford Model T came, and it just combined a bunch of technologies that were already there, but it combined them in a way.
Created a sweet spot that took off.
yeah, people looked at it and they said, oh, wait a minute, I think we may actually have something with all these individual bits and pieces that we developed. In the case of Bitcoin, there was developments in crypto and the internet and protocols and C++, software development technologies and tooling. And Bitcoin kind of made people say, wait a minute, I think we might have, something pretty radical here. But we don't all drive around in Model Ts. We have sports cars, and we have trucks and tankers, and we have cars that are optimized for different use cases. And XRP was the first cryptocurrency that optimized for a use case, and that use case is payments.
I see. So this is one of the issues about Bitcoin, is that it can take you, I guess it's not as bad now as it was, but for a while there, it took a very long time for your payment to go through.
Right, and Bitcoin's been working on higher levels to sort of reduce that delay.
Right.
Lightning Network is a good example.
Right.
Sort of my counter argument to that is, like, one of the things that most people hate about the current financial system is that we have these bottom layers that are ancient and inferior, and we've just been building Band-Aid after Band-Aid on top of them. Like, if you go to your bank's app or a PayPal mobile app or something, it's all glitzy and nice, but what's happening deep under the hood is that the money is moving on pipes that were built in the 70s. And it's sort of ironic to me that the Bitcoin folks have kind of replicated that same pattern of saying, well, Bitcoin is kind of slow and it may not have the transaction volume, but we can build a layer on top of it. I think the innovation at the very bottom should not stop. I think we can continue to build better lowest layers rather than putting Band-Aids on top of them. Whether or not those Band-Aids are successful, I think the better strategy, if we're going to build new bottom layers, let's build the best ones we can.
Okay, and that's your goal at Ripple, the company.
And I think it's still early days too. Yeah, and I'm not going to claim that like XRP is perfect and that those technologies should never change. I think that there's going to continue to be waves and waves of innovation, and to think that like Bitcoin is always going to be the market leader just because it has greater adoption or a greater market cap, I think it's a technologically driven industry, and it's still so early as far as what these things could do that I don't think there's any unsurmountable lead.
Okay. I've never asked you this, Phil. Are you sitting on a ton of Bitcoin? Are you some kind of really wealthy guy that I don't even know about?
No, I think it's a chair from IKEA.
I see. All right. So we should really talk about something. What's that?
I have no cryptocurrencies.
Ah, I see. I have a very small taste of some Bitcoin that I got a while back. What I was going to say is we should actually talk about something that you just touched on, David, and that was C++, the technology. Bitcoin is just a protocol. Could theoretically be written in any language or rewritten in any language and still interact with the existing Bitcoin, because it's just a protocol. As long as you behave properly on the wire, it doesn't matter what the software is. But in fact, the original Bitcoin implementation is C++. And my guess is that all of the original work for XRP also. Is that correct, David?
Yes, that's correct. The software that manages the actual transactions and the ledger is all written in C++.
Right.
Client tooling can be written in any language, and of course, you could re-implement in any language if you wanted to, but to my knowledge, no one's done so.
Right. Yeah, because you want that low level control with lots of performance. And what's the point in rewriting it? It's already portable, right? It already runs on whatever platform you want to run it on. Is that
right? I think so. I think the argument for re-implementing in another language would be if there was some sort of a bug or defect that caused, let's say, everybody's C++ implementations to fail in some way, the network could still continue if there was another implementation. But there's also risk if those two implementations disagree. You want every server to treat every transaction precisely the same, and so you run into the risk that there might be defects in the specification. But then the sort of counter argument is that if there are defects in the specification, we want to find out, and we don't want to hide it because there's only one implementation of that specification. I guess you can argue it, either way, and there are people who will argue it either way.
Sure. Well, I remember having this discussion with someone about what languages why was it that other languages didn't need to be an ISO standard? Why is there no ISO standard for Python? And I said, well, you understand that Python itself, there's a single implementation of Python. And so there's no question about what Python does. If you have any question about what this particular library function does, test it out, because that's the library function that Python is. Of course, they do document it, but they don't have to document it as rigorously as C++ is documented, because C++, of course, is going to be re-implemented multiple times. And so there has to be no question at all about what's the official interpretation of that implementation.
Right. And one failure I've seen again and again, ways that things go wrong, is people observe behavior in their compiler or their tool chain, and they assume that that behavior is guaranteed.
Right.
And sometimes it doesn't seem to them like there's any way that anything else could be the case. It just seems to them so obvious. Whereas to other people, it might just seem like, wow, that's a weird, we never even really thought about that. It just happened to do what you saw it do. And where you have a standard that's very rigorously and precisely defined, and where there's an iterative process where people say, hey, this is a little ambiguous. Some people think it means this, some people think it means this, and then there's a process to precisely define that. You know exactly what it is that you can guarantee, and that tremendously reduces the risk that someone will build their code on another compiler or a new version of the compiler or a new platform, new libraries, whatever. You want to know that they're going to get the same behavior. You want that high level of reliability, particularly where you have software that's handling billions of dollars worth of value, and where you don't have you sort of don't have a central operator to say, hey, try out this version, and like to coordinate changes. So that's a significant advantage for C++, and I think that that's an advantage that carries over into other applications as well, where you need this high level of assurance to know what you're actually supposed to rely on. I would contrast, like, the Windows platform in the early days was very poorly specified, and so we have a lot of code that relied on behavior that was never intended to be things that you could rely on, and the level of documentation has improved drastically since then. I think that's an example of why it is important to know what it is that you're supposed to be able to rely on, so you don't rely on something that wasn't meant to be reliable.
For a very short period of my career, I was I worked on a browser, a network browser, an HTML browser, and one of the guys that I worked with told me the story of tables, and he said the original implementation of tables was poorly specified, but people playing around with it found out that if you actually wrote bad HTML code, in other words, if you didn't close this tag, or if you did this or this, you would actually get the effect they wanted visually. And the problem was that, this was originally done by Mozilla, and Microsoft basically re-engineered that for the Windows version of their browser. I was on the Mac team, on the Mac version, and the engineer there said he had also had to re-engineer all these things because there were just so many pages that were taking advantage of stuff that was poorly specified. And he says the thing is, if you look at the HTML specification, which is of course now also an international standard, it doesn't say anything about tables, about how it has to behave in all these interesting situations. It only says, if you write everything perfectly, this is what it's supposed to look like. And in fact, people have been relying on, undocumented behavior that is actually replicated in browser after browser, where someone has to go in and re-engineer it.
Yeah.
What a disastrous situation.
Yeah, and I'm sure we could trade examples of similar disasters, but I think that's a good that's the good answer to why do you need a standard that's worked on at this level, where people all throughout the industry send representatives, they submit complaints about issues that they've had, and I think it's a testament to C++ life, how long it's survived, and the fact that we still have new improvements coming out to this day. The way threading was absorbed into the language, there's just example after example. The way the libraries evolved, I don't think there's any language that has anything similar.
No, I think that's I think there's, well, let me see if I'm actually correct here. I was thinking there were four languages that are international standards: C, C++. I can't remember what the others are. Maybe Fortran and COBOL or something like that. Yeah, and of course that's absolutely a requirement for long-term stability if you're cross-platform. Now that's the thing. As long as you have, as I was talking about with Python, there's essentially a single implementation. It gets ported to many different platforms, but the library itself and the engine, the interpreter engine, is a single implementation. And so you can kind of say, well, the standard is whatever the engine does. And we may rev that with version 2, but that means the standard changed.
Right, and you get this problem of two people could disagree over what's actually part of the standard and what's just the way this code happens to work, and that's what you really don't want. That's I mean, anyone who's been in the software development industry for more than a decade or two can tell you stories about cases where people just assumed something just seemed so obvious to them as guaranteed, and somebody else never intended it to be guaranteed, and then that behavior changed, and then things break. And where a breakage could mean billions of dollars of losses that are very difficult to recover,
Right.
you want to avoid that.
Yes. Well, that's your field. I mean, when I'm thinking about software, I think about, oh, there's a terrible thing, your app's going to crash. I don't think about, well, it's a terrible thing, somebody's going to wipe out your bank account.
Right. It's an interesting mindset where the worst case scenarios are significantly different. One of the things that I tell people is, like, if you have software that hasn't been developed by rigorous development techniques, you don't have good unit tests, you don't have good modularization. What you wind up having happen to you is that you have this software that's working and people are using it to move large amounts of money, and they're relying on it because they've been relying on it in the past, and it hasn't failed them. And so when you come up with a new version and you tell them, well, rely on this and see if it fails, that's not a good argument, where failure could be unrecoverable losses of large amounts of money. And even worse, the way these networks work, right? There's only one Bitcoin, right? Bitcoin is a single network, and everybody in that network wants to agree with everybody else so that the currency works. And so it's not like it's hard to have a controlled test. You can't say, like, I'll try this version of the software, and if it doesn't work, then I'll revert, because you trying that version of the software doesn't do anything if nobody else on the network is testing out any of the new features. So you have this problem of the necessity of a sort of coordinated network upgrade with huge penalties if things go wrong. And you can build test networks. The problem is test networks never replicate the complexities of the real world. Like, there's no test network for the internet.
Yeah, they're never at the same scale, right?
Right. So it'll catch the obvious, like, this doesn't do what it's supposed to do, but it won't catch the edge cases or the cases where you have vulnerabilities. So it's quite a challenging development environment, and it makes things very much slower.
Particularly a scale system. When I was at Amazon, we had a particular bug that was it was a performance bug, but it was a really nasty performance bug as you scaled. And as it was rolled out, literally within seconds, alarms were going off, and we stopped that, rolled it back. But we looked and said, what happened? We ran this on the test network. Well, the test network was only about 1/10 of the size. And when we looked at the numbers, performance did in fact fall, but not enough to set off alarms. It was, it was an impact within the noise of what we might have expected on a particular rollout of a new feature being added. But when it rolled out at scale, it just fell apart.
Yeah, and you also have a sort of malicious environment in the real world too. Like, once you go into production, there's sort of like a huge bug bounty of people. There are people who want to demonstrate that the system's unreliable. One interesting category of attacks that you have to think about are what we call algorithmic complexity attacks, where someone maliciously constructs data that causes your algorithm to perform in its worst case rather than its average or best case. And it takes programmers a while to get used to having to deal with an environment where all the data that they're processing is potentially hostile, and the attackers know all of the algorithms that they're using.
Is your code open source?
Yeah, it has to be, because
otherwise nobody would trust it.
Exactly, and also somebody would have to control it at that point. And the idea is that, like, let's say it was closed source and there were 7 people who had access to it, whatever. Like, they could force people to accept changes that those people didn't want, and then it wouldn't really be an open digital asset. It would be subject to some sort of centralized control. And the idea of the design of these systems is to guarantee that they'll do what their users want, because there isn't anybody who has some special authority to dictate how the software operates. And so being open source is table stakes at that point.
So I want to find out a little bit more about your background. You told us that XRP predates the Ripple company.
Yeah.
So but you were one of the original creators of XRP.
Right. In around October, November of 2011, Jed McCaleb, who had the original idea to look for a sort of distributed agreement protocol rather than proof of work. He was looking at what was happening with Bitcoin, and he saw that proof of work was expensive and inefficient, and he had this idea that you could use a sort of distributed agreement protocol, kind of like just having everyone participating in the network just sort of agree. And he hired me to see if he was right, if that was possible. And back then, number one, we didn't even know if it was possible. But even if it was, we didn't know what it would be good for. So we had no idea what it was we would be building. It just seemed as an interesting sort of technology to develop. And then around the end of 2011, the beginning of 2012, we discovered that not only is it possible to do that, but that it has some interesting properties that systems like Bitcoin don't. And one of them is just much more rapid confirmation. A Bitcoin transaction you can't be confident that it's going to occur for between 10 minutes to an hour, depending on network conditions and the size of the transaction. With a distributed agreement protocol, you can have that level of certainty in 5 or 6 seconds. So we started thinking, what use case would that be good for?
And the problem with that from a Bitcoin point of view is that, you know, if I make a deal with someone, sell them my car or whatever, I would like to be able to just show up, look at the car, sign the paperwork, and move on. But no, this is a substantial amount of money. We both got to sit around and drink a cup of coffee while we wait to make sure the transaction cleared. And that's a little annoying.
It's kind of funny too, because it sounds crazy now, but at the time, myself and a lot of other people thought, you know, an hour is not bad. Like, you know, currently payments take a couple of days. What's wrong with an hour? And it's a lack of sort of forward thinking, right? To think that, like, one of the things that, like, if you look at internet traffic today is thousands and thousands of times what it was in the past. It's not because we're doing more of what we used to do. It's because we're doing things that are completely different. Like Netflix couldn't have existed in the past. You have to have an internet that has some absurd level of traffic capability for Netflix to exist. What we're interested in are what are the payments that aren't happening today because the existing payment systems can't handle them. They're too expensive or too slow. That's where the growth is going to come from. Yeah, it's great to do today's payments faster and cheaper, but if you want to, like, grow the market and grow the economy and improve things, you need to make things so much faster and so much cheaper that you can have sort of ubiquitous payments. If I walk through my neighborhood, there's probably all kinds of stuff going on the internet, like as I walk by, people, motion detectors, cameras. Like, could you imagine if there were like thousands and thousands of payments going on in the background? You might pull up a web page and it might pay for its micro hosting for that very web page. It might pay a database for news that I'm interested in. It might pay some other system to get my preferences, to find out who am I, what am I interested in, what ads would I be most receptive to. Like, you could have thousands of payments going on in the background completely invisibly, just like we have data traffic of all kinds invisibly. Like, what world does that build?
Yeah, no, I think of this as having huge implications for basically replacing advertising.
Yeah.
I mean, I don't want to read ads. I don't want to have ads bother me when I go to a website. But the alternative is I also don't want to have a subscription to every place that I want to read, because a lot of the places I read, I don't know I'll ever want to come back again. I'm testing it out. And, you know, maybe I want to read 2 or 3 articles before I want to make a commitment. But on the other hand, if I paid half a cent for every web page I read, that would probably pay for the web page. But who's going to pay that transaction, right? I mean,
exactly.
am I going to take a credit card bill of half a cent? Maybe I wouldn't mind, but the credit card company is going to charge the seller more than half a cent to process.
Exactly. That's probably like one of the most obvious use cases, because the advertising model is so badly broken and everybody hates it.
Well, I'm all about obvious. What can I say?
Yeah, and you know, it's hard to know what the real use cases are. Like, if we had theorized about email before it existed, we said, what are people going to use email for? We would have been completely wrong. We would have said, like, oh, the same thing that they use postal mail for, but if it's not really personal and you don't need to, like, have it handwritten, and as long, you know, but people use email for things that they would never use postal mail for. And so it's kind of the same thing. It's hard to imagine what the future use cases will be, but I think ubiquitous micropayments, where payments are essentially instant and essentially free, like on the order of the cost and time of a DNS query or something, or getting a web page, it's going to change the world. And I don't think we know completely. You know, I don't think we can say how.
Right. I think the big example of that is when radio was first rolled out. People said, "Who's going to pay for a message to everyone?" Right? I mean, it just people just couldn't figure that out. It's like, well, how are you going to pay for this? Yeah, great. You can play music to everybody out there. Who's going to pay for that? And it had to, you know, and then it turned into a huge thing.
Yeah. I think there's a general consensus among just about everybody in this industry that we're on the cusp of the next big thing. We just don't know, like, who the players are going to be or what the technologies are going to be. You know, like if you had thought of search around in the early days of the internet, But you know, would you bet on Google, or would you bet on Lycos or Alta Vista, or like there were winners and they won big, but you know, there were also losers who didn't get any share of that. I think that we're drastically changing the way money moves. We're drastically rebuilding those lowest layers, but I don't think we know what are the use cases going to be, what are the technologies going to be that work. Like I don't think we know that yet. Obviously, I hope it's the company that I work for, but you know. I think the technology is still early too. I think we've started a chain of technological development where if you think that today's technologies are what's going to do it, I think you're probably wrong.
Right. Well, you know, I used to work at Amazon, and they famously quote Jeff Bezos as saying, "This is day one. We're so early on." I mean, it sounds like, oh, you know, it's already shaken out. We know that Google's the big winner. It's possible that 30 years from now, people are going to say, Google who? I mean, you know, the internet is just, it's, you know, those of us who have gray hair think that, you know, we've seen it all, but the truth is it's just going to keep coming, and it's going to be more, you know, more of everything we see. And we don't know that changes, qualitatively changes. It's not just, oh, I get my email twice as fast. No, something qualitatively changes when you get to a certain point. Things that didn't make sense before start to make sense. And
it makes this a very exciting area to work in too.
Yeah. All right. So there was kind of this theoretical problem you were solving, which was, can we make, so what is the role of proof of work? What does that mean for Bitcoin? What does that mean? What is that about?
That's one of the most frequently misunderstood things, and I think understanding that clearly is very important. So if you run a node on the Bitcoin network, you download the software and you run it, you enforce every rule. You don't need to ask somebody else if a transaction is valid. You don't need to ask somebody else what a transaction does. You enforce all of those rules independently. And it would be great if we could do the entire system, every little bit of it, just by having every single participant enforce every single rule. It would be perfectly decentralized. Nobody could ever trick anyone because everybody would check everything. The only thing that you can't do that way, and there's exactly one thing that you can't do that way, and that's solve what we call the double spend problem. So if I have one Bitcoin, I have to be able to send it to Alice, and I have to be able to send it to Bob. But if I can do both, we have a problem. So somehow, by sending a Bitcoin to Alice, I have to be prevented from sending that same Bitcoin to Bob. And you can reduce that problem to putting transactions in a global order. If we all agree that the payment to Alice comes before the payment to Bob, then we can all agree I don't have the Bitcoin anymore and the payment to Bob is invalid. The problem is in a network that doesn't have a central authority, doesn't have a perfect timekeeper that everybody has access to, there's no easy way to guarantee that everybody processes transactions in the exact same order. And that's
so I could send out two separate orders to two separate people and essentially double spend my coin.
Right. And so we need some way to have eventually have a global agreed ordering. And until such time as I know that everybody is going to agree that the payment to Alice comes before any possible conflicting payment, Alice can't rely on having received the Bitcoins. If you want Alice to be able to, receive a Bitcoin and mail you a book or do some work or something, there has to be some point at which she's confident that everybody will agree that that payment to her comes before any possible conflicting transaction, even one she hasn't seen. That's what
where the delay. That's where the delay comes in.
Correct.
Because we're waiting for that confirmation. Okay. So how does that confirmation happen?
Well, in Bitcoin, it's actually quite complicated. But what happens in Bitcoin is proof of work is literally it's proof that you've done an enormous amount of work. And the system has a set of incentives to incentivize people to build a single chain of transactions. So if I want to build another chain of transactions that's different from the one that everybody else is building, mine won't be the longest chain unless I'm doing more work than the rest of the world put together, and the longest chain wins. So if you want to make money, you have to extend the longest chain. Essentially, it creates a reward for extending the longest chain.
So that's why we have consensus, right? Because if I said, oh, I like this other transaction, then I'm building on a shorter chain, essentially.
Correct.
We all agree because we all want to be building on the longest chain. So we all have an incentive to agree.
Correct. That's exactly right. The only problem is until that chain is significantly longer, it's hard to be sure that it will remain the longest chain. So eventually, and typically an hour is... Sometimes it is longer though, like the Bitcoin blockchain, because generating mining is what we call a Poisson process. It's like, it's completely random. It could go long periods of time without generating a block, and you could have time periods where you could go an hour and make no forward progress. It's possible. So it's a sort of statistically random process, but it will eventually provide you whatever level of certainty you need. just by people extending the longest chain. The downside of that, other than the fact that it takes so long, is that it has to be really expensive to extend the chain, because if I make $1 million payment and the chain is only $50,000 longer, well, you could have secretly mined a longer chain, and as soon as I rely on that payment, you're going to release the longer chain and undo it. So it doesn't provide any sort of definitive point of finality, and it's necessarily expensive. Its security is proportional to how much it costs to operate. The negative case for mining, if you wanted to make the negative case in the most cynical way possible, you would say that the security of model of Bitcoin relies on honest people actually spending more money than dishonest people might be willing to spend to disrupt it. And that's kind of what we realized in 2011 was probably not the best possible security model.
All right. So if I can summarize this, what happens is the miners are essentially building a chain by creating this plausible set of, they take all the transactions that have been sent, they put together a chain of transactions, and there's some crypto magic to come up with some kind of hash or something like that, which says this is valid. They send it out. Everybody verifies that the hash is consistent with the transactions they've seen, and when they see that, they vote for it. And when you have a majority voting for it, it becomes accepted.
Well, they don't.
Like that.
They vote for it by adopting it themselves and continuing to build on top of it. And so, what eventually happened in the case of like the payment to Alice, eventually Alice is watching the longest chain, and she'll see the payment to her in that chain, which means the payment to Bob could never go in that chain because a chain can't conflict with itself. Nobody will accept an invalid chain. Everybody knows that. Once the chain that contains the payment to her, that payment is sufficiently deep in the chain. Let's say the chain has extended well past it. It's extremely unlikely that some shorter chain will suddenly grow to be longer than that chain, because everybody working on that shorter chain makes no money unless they actually do make it longer. So you need some sort of mass conspiracy.
So in theory, the risk to Alice is that if there's a chain and the last transaction in the chain is Alice's payment, someone could take a chain that was one transaction before that and put in Bob's payment. And that's why she has to wait to see that her transaction is far enough back.
Right. The cost to do that goes up over time. And so she waits until the cost is high enough to make her comfortable.
And the cost is entirely in processing power.
Yes, that's exactly right.
Okay. All right. So what's the alternative? What's the ripple?
Well, so the alternative is to use a system that's sole purpose is to order transactions by a process that we essentially call distributed agreement. So it kind of works like this. I'll try not to get too technical. So first of all, transactions are basically just numbers. So you can just simply sort them. So in a batch of transactions, you can order them just by sorting them. So if we could agree on which transaction to process in batches, we could solve the sorting problem just by simple sorting rules. So what we need to do is we need to agree on which transactions to process in batches. And so the rule is that transactions have to be valid, they have to pay an adequate fee, and they have to be received on time. So if a transaction passes all three of those criteria with flying colors, there's nothing wrong with it. Everybody's going to agree to include that transaction in the batch anyway, everyone honest. The problem that you have is like a wobbler, because we don't have a universal source of time. So say there's the case of the payment to Alice and the payment to Bill. Let's say you saw the payment to Alice first and someone else saw the payment to Bill first, and so Bob first. And so we disagree over which one of those should go in the batch. All you have to do to fix that is two things. So number one, if a transaction is a wobbler, if it's sort of maybe okay, maybe not, agree to defer it into the next batch. And then the next step is if a transaction gets deferred and it's still valid, every honest person will include it. I don't know if I explained that clearly enough. I'll try it a little simpler.
Well, but yeah, go ahead. Give it one more try, and I'll ask a question.
Okay. So the network as a whole agrees to process transactions in blocks, in chunks of transactions, and everybody proposes what transactions they think should go in that block. And then if there's not supermajority support for a transaction, everybody just sort of withdraws that transaction. And that's how you preserve agreement. So let's say you and I disagree. You like the transaction to Alice, I like the transaction to Bob. What we can do is we can both agree to defer that transaction for one round and then use a deterministic rule to sort them. So all we have to do is agree that we're disagreeing, essentially. Once we agree that there's a disagreement, all we have to do is use the deterministic rule to sort them.
Well, it's a little bit more than just you and me. It's you and me and Phil. There's a bunch of people. And we all send out and say, these are the transactions that I know about and I like.
Right. And then the first step,
anything that, and we take the intersection of all those.
Right. And if there's a transaction that doesn't have, so if a transaction is perfect in every way, it will have like 99%, everyone honest will be voting yes on it, assuming, they're properly operating. So there's no problem. Where you have a problem is where you have a transaction that has some sort of reason why it might not be able to get supermajority support. Maybe it was received late, maybe there's a conflicting transaction. And all you have to be willing to do to preserve agreement is if there's a transaction that's sort of like a wobbler that has some issue, just agree to defer it to the next round. If it's not valid, let's say the payment to Alice has 99% support and the payment to Bob has 1% support. Everybody's going to say yes on the payment to Alice, and then the payment to Bob will get deferred to the next round, but then everyone will agree it's not valid next round because the payment to Alice invalidates it. So all you have to do to preserve agreement is be willing to defer a sort of wobbler transaction to the next round. That's really the only mechanism you need to keep the network in agreement, because all the state is public, everybody enforces every rule, everybody knows what every transaction does. You just need to say, hey, there's some disagreement over this transaction. We need to subject it to deterministic rules rather than trying to agree on it.
And there's two advantages to that. One is that it can be faster.
Right.
And the other is that it's not burning down the Amazon forest to power the machines to do it. It's less expensive to do.
In the 99% case where there's absolutely nothing wrong with a transaction because it was submitted by an honest person who signed it properly and has the correct, fees and everything, then we'll just rapidly reach supermajority agreement on the transaction. And so in the normal case where someone is not doing anything malicious or trying to trick the system, they can have absolute confirmation on the transaction in 5 seconds or so.
Now, given that the time of a transaction is so important, is it a coincidence that Howard Hinnett, who also works at Ripple, has created a time library to submit to the standards committee? Is that a coincidence?
It's interesting that the biggest problem with these types of distributed agreement protocols and these distributed networks is that you don't have a sort of universal source of time, and there's a lot of code inside the XRP ledger logic that deals with time. And also when you're managing priorities and you're receiving queries, you're trying to keep up with the network, you're trying to get things done. Yeah, there's a lot of his work at Ripple had to do with the time code inside it and fixing some of the issues with that. It's gotten really nice, I have to say. The ability to have constants that have units in them is just really nice, and the ability to know what you're guaranteed by the platform. Because another problem that you'll sometimes have is like some platforms will have more accurate time sources and some will have less accurate time sources, and you can find your code behaves unpredictably when you compile it on a platform. Having your choice of clocks that have different behaviors. And I guess the other one that's near and dear to my heart is, do I want a clock that's as accurate as possible, or do I want a clock that's guaranteed to flow at a constant rate? And it turns out that the designs of those two things are very different, and people try that. I used to build GPS-based clocks and sell them a while ago, and time is kind of something that I was very interested in. Howard and I have talked a lot about that.
So basically, Howard just has too much time on his hands.
Oh no!
We just can't manage it well enough. Is the problem? We just need better tools to manage our time.
Going back to where you were saying that, assuming everyone or most people, 99% of people are honest and engaging in honest transactions and everything works smoothly, does that mean the system is open to abuse by people not necessarily trying to cheat anyone, but just trying to overload the system by all the extra bookkeeping involved in the conflicting transactions?
Yeah, and we had to do a lot of work on that. Our initial implementation of that sort of flood prevention or denial of service prevention I thought it was good enough, but it was not. And the new system is much, much more sophisticated. And so what it does is it monitors the actual performance of the network to determine how quickly it can reach agreement and how many transactions it can process. And then it ratchets up the fee required to even relay a transaction into the system based on that rate. So if let's say the system is clearing 1,000 transactions per second, and so what we do is if we get more transactions than that, we demand the transaction pay a higher fee before we even repeat it to other servers. So if there's just a massive flood of garbage transactions, they get stopped at the earliest possible level. If a server is relaying transactions to you that don't pay the appropriate fee, you can just break your connection to it.
Now, when you say the system, this is entirely a peer-to-peer network.
Yeah, it's emergent behavior.
There is no central system.
That's right. It's emergent behavior. Yeah.
Right. Yeah.
And so if the system gets a huge backlog of transactions, it actually becomes more efficient. It's hard to explain why, but what happens is processing 100 transactions at once is not 10 times as expensive as processing 10 transactions at once. It's a little bit less. So the system becomes more efficient when it has a significant flow of transactions, and then it will adjust the fees down to handle that. So it actually has a fee regulator that controls the admission of transactions into the system. Also, the distributed agreement protocol allows you to say no to a transaction by doing nothing. Essentially, by not voting yes, you've implicitly voted no. So if a large number of transactions like get into one part of the system, like before the fees can go up, other parts of the system will implicitly be saying no to those transactions simply by not processing them, simply by not acting on them, and then you'll quickly realize that there isn't majority support for them. We actually put a significant amount of effort into exactly that. Bitcoin uses a similar scheme. It has a fee in each transaction, and if each server makes a decision when it receives a transaction whether to repeat it to the rest of the network or not. And the test is the same. Like, do you think this transaction will successfully be able to pay a fee? So if you want to flood the network with transactions, you have to flood it with transactions that the network thinks will each claim a significant fee. And if the transaction can process 1,000 transactions a second, if you want to flood it with transactions, you have to pay that fee on each transaction, whereas an honest person just has to pay a greater fee on one transaction. Someone analogized it to trying to smother a campfire with $50 bills. Yeah, it's annoying, but you can always light another campfire. So while you're flooding the network, if you want to lock out my transaction that I'm willing to pay $1 for, you have to pay $1,000 a second to keep me locked out. And then all I have to do is pay $1.01 to get my transaction in. So I can just sort of sit back and let you waste $1,000 a second delaying my transaction. Everybody else is kind of happy that you're doing this because your ability to attack the network is going down as you're expending these resources. Your store of however much funds you have, is being depleted. But if somebody wanted to put enough money and they said, I want to prevent the network from making a payment on January 17th at 3 p.m. and I want to delay it to 3:02 p.m. and they had the funds, they could push the transaction fee up for that precise time period. And there's nothing you can do about that because there's no central authority to say, hey, these transactions are worthless. Like, 3 people moving funds in a circle looks like economic activity. There's no way to tell that, all of those accounts are conspiring. So you just have to hope that like the fees are greater than whatever reward they might get out of doing that.
There's always an arbitrage opportunity.
Yeah.
But in that case, it wouldn't be as much arbitrage as you have some reason to just delay the transaction.
Right. And you could imagine some situation where like there was some tremendous financial reason for me to delay it. Like if I could delay your transaction from 3 o'clock to 3:02, that there'd be some tremendous like economic benefit to me to do that. But the thing is, all you have to do is pay more for your one transaction than I'm paying for each of the 1,000 transactions a second to lock you out, to push the fee up. So it's hard to come up with a realistic attack scenario. But again, people who use the system should understand the circumstances under which it's secure, and exactly you want to make sure like you don't want to enter a contract where like I owe you $1 million if I can't make a payment at this exact time, because then it might be worth it to you to attack the network. So you would put in some clause that says like if the network is not functional at that time, or you just have to understand that there isn't a central authority that can provide you an absolute performance guarantee. It's an emergent property of the system that people could abuse if they wanted to.
So getting back to Howard, and you mentioned that you've talked to him a lot about time, but what I'm wondering about is, have you talked to him about the standards committee? Has your understanding and appreciation about what the committee does, has it evolved by talking to Howard? Has he given you insights?
Well, they say that people who like sausage and respect the law shouldn't watch either one being made. I don't know how much I mean, yeah. The most common frustration that I hear, not specifically from Howard, is that people are sort of trying to defend their implementations or their use cases more than they're trying to like evolve a functional language for everyone. But other than that, I hear mostly good. I hear lots of good things. I know it's very popular on your podcast to criticize the standardization process. I've generally been pleased with the progress that I've seen, particularly on the threading issue, where that was just there was no work on that at all. The work with the move semantics and unique pointers. That's really good. That's great for us because we have a system where you have data that's manipulated by multiple parts of the system. So like you have some data that might just be created, a transaction might be operating on it, people might be querying it. The ability to manage the ownership of that object in a controlled way in a multi-threaded environment is really nice. And I have to say the biggest thing for us that I credit the committee for is the ability to have code that behaves complex classes that have value semantics, by which I mean they work just like an integer. Like an integer is really nice. If I pass an integer to you, I know that you're not going to modify it. I know I can copy it. It's very cheap. Like it has this behavior that's really nice and easy to reason about. And the ability to build complex classes that have that same type of behavior through move semantics, where I know I'm not going to get a deep copy unless I actually need one, it's fantastic.
No, I do agree, although I'm not going to name any names, but there was someone on Slack who was pointing out that they think that there are people in the standards committee who don't understand what value semantics are, and that's why we get things like span and some of these other classes that are questionable from a value semantic point of view. And I think there's a role for something like span. I really do. I'm not saying it's a terrible class, but I would think that anyone, how do I say this correctly? If you're on the standards committee and you're making a decision about something like should we accept this type into the standard library, I really, really hope you understand value semantics. I'm not saying that there's no such thing as a reference class that you'd want to make, which is essentially what the span is, right? It's a reference class. And I'm not saying there's no role for that, but I'm saying you should understand the difference. You really need to understand this. And I think I think there are, as I say, people on the standards committee who think that other people on the standards committee may not really understand that. And that's a little, when you say that we're critical of the standards committee, you have to understand we come from a place of love on that, right? It's that we want to hold ourselves to a very high standard, because part of it is when the standards committee screws up,
we all pay the price. I mean, let's face it. Right?
It's not just the
developers on down.
We always pay it. We keep paying the price, right? Once it's hard to come back from that. Sometimes the committee can say, like it did with, say, auto braces, where they said, okay, we were wrong. We're going to change what that means. But that's not often what they do. And, we still have vector bool, right? I mean, it's just, you have to live with it.
Yeah. Yeah, I mean, that's the plus and minus of having a language that has like a formal process by which changes are adopted. It's great when it works, and it elevates the stakes, right?
Yeah. Well, I mean, it's easy to mention vector bool. It's easy to mention all the problems, but when you look at it and you see what's been accomplished, it's not clear how it could be done much better. If it was left entirely in Bjarne's hands, it would be very different. And some things would be better, but many things wouldn't be as good. I mean, the committee it's maybe not the only solution, and maybe it's not the best solution, but it's a pretty good solution, but it is still a solution that's going to cause errors, because any solution is going to cause errors, right?
Right. And I think it's important that we do criticize what we don't think works well. The same way when you have a team that's developing code, just like when you have a committee that's developing a standard, it's hard to know ahead of time what processes are going to work and how well they're going to work, and you need to be iterative on the process, and you need to be critical of performance. What are you doing that's working? What are you doing that's not working? And I agree that the criticism does come out of a place of love. I mean, we want the best possible standards. We want the language to continue to evolve and to maintain the features that we love about it. And I think we just need to be very open and have those discussions about what's working and what's not.
We have some great success stories from that process as well. I mean, look at auto pointer. Had a lot of problems, but was an important stepping stone towards move semantics.
Yeah.
And now we don't really have auto pointer at all anymore, technically. But we do have move semantics.
Yeah.
Definitely a success story. Definitely makes the language easier. I mean, once you pay the price of learning move semantics, which of course was a little annoying for everybody, particularly people who'd used the language for a while, but now like the benefit that we get out of that from being able to manipulate complex classes without having to think about as much about what's going on under the hood is just phenomenal.
Phil, did we make all the announcements we were supposed to make? I think
we didn't make any announcements.
I think I jumped the gun on the announcements, didn't I? What do we
Before
want
we
to
get to
talk
the
about?
announcements, there was one question from the chat that I think it's worth putting to David.
Okay.
Because we started off talking about the high reliability, and Matt was asking if he's found any particular good methods that are underused in the context of C++, like formal verification or bounded model checking. Is there anything like that that you do to increase the reliability?
I guess test-driven design, unit testing, making the code very modular so that you can test the pieces. I'm trying to think. Formal verification, I think it's kind of early for that. I don't think we have. I don't think we can formally verify much of what we do. Monitoring performance, testing on real workloads, those kinds of things. I don't know that I have a really good. I don't know that I have a good specific answer to that.
Okay. Well, you mentioned testing. That's a good start.
Yeah.
Any particular test frameworks, by any chance?
So we actually mostly use the one that Vinny developed. That's the part of Beast.
Okay.
It's pretty simple. It basically just drives the unit tests and collects the statistics back, monitors performance as well as in terms of resource usage as well as correctness. But test-driven design is extremely important. Like the scenario you don't want to get into is where your code is reliable because people have been relying on it and it hasn't screwed them. That's kind of the mistake that we made in the early days, and we had to re-implement and modularize and refactor a lot to get our code to the point where we knew exactly what guarantees each piece of the code was supposed to ensure. You definitely don't want to get in that pattern. So if you're not developing that way, you're not producing reliable code. It doesn't matter how good you are at it. You're not going to.
It's kind of interesting, and I want to thank you, David, for stepping in on such short notice. But the guest that we were going to have, Michael Feathers, has talked about this. He's written a book, and I don't want to talk too much about it because we are going to get him on, and so we'll explore it more on that episode. But what you're talking about is exactly his point, which is that you need to be able to have those kinds of tests in order to have reliability. Because in fact, he actually he wrote a book called Working Effectively with Legacy Code, and in his book he defines what legacy code is, and he says it's code without tests. And the first time I read that, I thought, well, that's a silly definition. And then as I thought about it more, I said, that is an incredibly insightful definition.
Yeah. Yeah, and those tests also serve as sort of documentation of how the code is intended to be used, which can sometimes be helpful. The cases that it was expected to encounter, and of course, how it was expected to behave in those cases. It's very, very difficult to modify, optimize, debug, or troubleshoot code when you don't know what it was supposed to do, and you have to sort of infer that from how people are using it. I mean, that's obviously, and I agree, that's very insightful. Like the problem code is the code that doesn't have that. That's where you have a problem.
Right. So I think there was one other, I guess not a question, it's someone called me out. I said there's one Python implementation, and I've been corrected by, is that Juicy? I don't know how to say it. No, he says there's 4. There's CPython, Jython, JPython, IronPython, and MicroPython.
Hadn't heard of MicroPython. It's a new one.
But yeah, okay. I'm not sure that the point I made about that is actually invalidated by the fact that there's multiple implementations, but it is true that there's going to be that's going to help. It's going to force people to be more rigorous in defining what the implementation is supposed to do when people make alternatives. What else do we want to talk about? Oh, we want to do a conference roundup. I'm not sure how many things have changed. Anything changed with C++ on C?
Just that the Twitter competition that I announced last week for winning a free ticket, if you tweet about it, I had 60 entries for that, and randomly pulled a winner yesterday. I've got the whole process on the blog, and the winner was actually Kate Gregory, who's also one of my keynote speakers. So that was a bit of a turn up. But she had promised to give it to someone else who needed it. She said she's going to work out what that means.
I was going to say, you don't give a free registration to your keynotes. That's an interesting thing to explore.
Yeah.
That's terrific. That's terrific. So Pacific still has tickets open. CPPCon. Our big news, but I think we talked about this already, is the field trip, or maybe we didn't talk about. I don't think we actually had the field trip announced last.
You teased it last week.
I teased it. It is now. It is Cougar Mountain Zoo, and that's just a fairly short bus ride away from the Maidenbower. And in fact, it sounds like a lot of fun. When they were proposing this, they put this proposal together. My first thing was, well, is one afternoon enough? Because it looks like there's a lot of good stuff to see and do there. So that's the new thing there. I don't know that we have. We do have one more. We need to tease something else, don't we?
Oh yeah. So are we ready to say much about it yet?
Go ahead, say whatever you want to say.
Well, you teased this a while back, I think. This idea of we're calling it tool time. Yes. The idea of just one evening during CPPCon, we get a load of people in a room who will represent different tools. So that could be a software tool, an application. It could also be a library or a framework. And if you represent that tool, or you're just a super user of it or something, you can set up a little table there, and people can come and ask you questions. You can do demos, a bit like the exhibitors might do on their booths, but this is just open to anyone. And I think we're now ready to announce the details on that.
Right. And so you don't have to be an official representative. You don't have to work for the company. You don't have to be the committer for the open source, whatever. You're just someone, as you said, a super user, somebody who knows a lot about it. If you are excited about, continuous integration and you want to talk about Jenkins or something like that, love to have you represent Jenkins.
Yeah, that's right. And I think a while ago you were saying you had someone in mind to run that. It turns out you were talking about me.
That's right.
Short straw.
Congratulations, Phil.
Thanks. So there is a page about it on the CPPCon site, but I don't think you've linked to it yet, have you?
No, I don't think we've officially rolled it out. So we need to make an announcement and get that linked. However, people can reach out to either one of us if they really want the early scoop. But I hope by Tuesday we'll have an announcement up.
Possibly by the time the podcast goes out.
Because what we are going to ask for is for people to let us know in advance so that we can figure out how many tables we need and figure all these things out. So we do want anyone who wants to represent a tool to contact us and say, here's the tool I want to represent, and so that we can prepare that.
Yep. So you heard it here first.
Yeah. Well, again, I want to thank you, David, for stepping in on short notice. It's been a lot of fun. Obviously, this is a big interest of mine, and I'm really, really pleased to have your insight. And thanks a lot for coming in on short notice.
Thanks for having me. It was my pleasure.
Alrighty. And I want to join you and Phil in wishing everybody safe coding.
Safe coding.
Safe coding.